Let's write a C program to find prime numbers from 2 to n using a method called Sieve of Eratosthenes. Sieve means it's an utensil which we use to separate things we want from things we don't want. Eratosthenes is a Greek mathematician. You can spell his name like this, Eratosthenes. Okay. So I take n as 101 because we have numbers from 0 to 100, which makes 101 elements. Also, one thing I'll clarify now itself, these numbers 0 to 100 represent index numbers and not the content present at those indexes. Okay, the contents are 1 and 0, which represents 1 represents prime number, 0 represents composite number. Okay, so the first prime number is 2, so we will start from index 2. I'll also write snippet of codes here while explaining the Sieve of Eratosthenes method to find prime numbers. So I'll take a for loop and initialize I to the first prime number, which is 2. And for each iteration, we check if I is less than n. Less than n means less than 101, which means 100. We can optimize this condition and I'll show that to you later on in this same video. Also, for each iteration of this for loop, I'll increment the value of I by 1. So now let us see the Sieve of Eratosthenes method. So the first prime number is 2. Now we cancel all the multiples of 2 present in this table. Remember, all these numbers are indexes and not the content present at that index. Okay, the content is 1 and 0. 1 represents prime number, 0 represents composite number. So we shall also log the first number struck by the selected number, the number which is selected by this for loop. The first selection is 2, right? So let us log the first number we strike out, which is 4 in this case. The first multiple of 2 is 4, that is 2 plus 2 is 4. So 4 plus 2 is 6. 6 plus 2 is 8, 8 plus 2 is 10, and so on. So the first number we struck is 4. Let us log that. I'll tell you why we need to do this. Now let me strike all the numbers which are multiples of 2, which means the previous number we struck plus 2. That's it. So I'll strike all the numbers which has 2 as its factor. If you can observe the pattern, all the numbers are plus 2 from the previous struck number. So all the elements in these rows have been struck off. Now I plus plus gets executed in this for loop. So the I value is 3 now. Let us see the first number struck off by 3. 6 has already been struck off by 2, so that's not the number. So 9 is the first number which was struck off by 3. So let us log that information here. So now let's go ahead. 9 plus 3 is 12, which is already struck off. 12 plus 3 is 15. 15 plus 3 is 18. 18 plus 3. I'm adding 3 because the number selected by this for loop is now 3. So let me go ahead and strike off all the numbers, that is all the multiples of 3 now. So this striking off represent that we are storing 0 at these indexes we are striking, right? So that's the logic. So let me quickly strike off all the multiples of 3. Okay, that's it. So the next number which is not struck off is actually prime number, that is 5 in this case. 2, 3 are prime numbers and 5 is prime number because it's not struck off by any elements, any number which came before that, before 5. Okay, so 5 plus 5 is 10, which has already been struck off by 2, and 10 plus 2 is 15, which is already struck off by 3. So these are multiples of 5. So 15 plus 5 is 20, which already struck off by 2. 20 plus 5 is 25. This is the first number which has been struck by 5. Let us log that information. Now let me quickly go ahead and add 5 to 25 and strike all the multiples of 5. So the logic we are using is we add 5 to the previously struck number by 5. That also gives multiples of 5, okay? 95 and 100. That's it. So now, which is the next number which has not been struck by previous numbers? That is 7. So let us select 7 and see which number it strikes first. So 7 plus 7 is 14. So let us check that. 1, 2, 3, 4, 5, 6 and 7, which has already been struck by 2. 14 plus 7. 1, 2, 3, 4, 5, 6, 7. It's also gone. 1, 2, 3, 4, 5, 6 and 7. It has been struck by 2. 1, 2, 3, 4, 5, 6, 7. It's been struck by 3. 1, 2, 3, 4, 5, 6, 7. Struck by 2. 1, 2, 3, 4, 5, 6, 7. Okay, 49 is the first number struck by 7. Let's log that information. 49. And I'll go ahead and quickly strike all the multiples of 7 by adding 7 to the previously struck number by 7, okay? 77 plus 7 plus 7, and that's it. Now after 7 we have, all these are prime numbers by the way, we have 11 which has not been struck by any of its previous numbers, but as you can see the multiples of 11 are 11 into 2 is 22, and then 33, 44, 55, 66, 77, 88 and 99. All these numbers are struck off. And take any number which are not struck by its previous number in this table, and it doesn't have any multiples left without striking until 100, of course. So we have a logic here. We can derive at a logic here. So the max number is 100. Take square root of it, which is equal to 10. So you need to check only until this number 2 to 10 to get prime numbers up till 100, okay? That's the analogy we can derive at by looking at the procedure we just followed. So take any number which is not struck. Try to find any other number which can be multiplied by that number. You won't find any number till 100, okay? So if you do this method from 2 to 10, yes, 2 to square root of maximum number, which is 10, then you will get all the prime numbers till 100, that is n in this case, okay? That's the analogy we can arrive at this stage, okay, after analyzing this chart. So now let me give you a snippet of code, that is, I'll show you designated initialization here. So a of n is equal to, it's an array, assign 1 to all the elements at position 0 to n minus 1. So how you will do that? So 0 followed by 3 dot and n minus 1 is equal to 1. So that stores 1 at positions from index 0 to n minus 1. Okay, these are the indexes you are seeing in this table 0 to 100, okay? So in that index we have 1 now. All the index has 1 as its value right now. Now let us take this analogy and modify our code, that is optimize our code. So this condition becomes, so let me take a integer variable and num and take square root of n. In our case it's 101, so it will come to 10 point something. Since it is num is integer, the value of num will be 10. So let me remove this n and only iterate this for loop until square root of n, which is stored inside num. So that's a huge optimization to this code. Okay, so remember, if the maximum number is 100, square root of 100 is 10. So if we check from 2 to 10, we will get all the prime numbers from 2 to 100. So now every element is 1 from index 0 to n minus 1, right? So we will check that if a of I is being selected by this outer for loop. So if a of index I, so the value of I is selected by the for loop, is equal to 1. So initially we consider all the elements as prime. So we store 1 everywhere in this array, okay, from index 0 to n minus 1. So let me close this. Let me close this if condition. So now let us check. That is, let us store 0 at the place of multiples of the number selected by outer for loop. So at first I will be 2, right? The first number to be struck off by 2 is 4. So what's the relation between these two numbers? That is 2 raised to 2, 3 raised to 2, 5 raised to 2, and 7 raised to 2. So the first number being struck by 2 is square of that number. So j's initial value will be I into I, which is I square. Okay. So let us iterate this inner for loop until j is less than the maximum number, which is n in this case. Less than n means less than 101. Less than 101 means 100. Okay. So this is very important, the last part. So j need to increment by I, that is, we need to add I to the previous value of j. So j is equal to the initial value of j plus I. So what's the initial value of j? Square of I, which we write like this, I into I, which is I square. Okay. So initial value of I is I square plus whatever is present inside I. So the value of I is selected by outer for loop. Okay. Hope this is very clear. So don't move any further if this thing is not clear. Pause here and track the values of I, j, and a of I. Okay. A of I has not been modified yet. So track the values of I and j here. Okay. So if it's clear, then move further. So j selects all the multiples of I. So I'll store 0 at a of j. So that's it. That's all we need to do. So this would give prime numbers, all the prime numbers from 2 to n. So whatever the values which are not struck off, that means technically the array elements which has 1 are prime numbers. So let me clarify once again, the table you are seeing here 0 to 100, these are indexes, index numbers, and the content of these array is only 1 and 0. 1 represents prime number and 0 represents composite number, and we are interested in prime number. So I'll print the elements, the index of those elements which has 1 as its value. So if a of I, the content present at position I, is equal to 1, that means it's the index value, the index number is prime. So I'll print the index here, /t for tab character, and I. The index value is present in I. Okay. The content of these elements are only 1 and 0. 0 represents composite number and 1 represents prime number. So a small recap, n is equal to 101 because we have numbers from 0 to 100, which means 101 elements. Now look at this outer for loop. I is initialized to 2 because 2 is the first prime number, and this for loop iterates until I is less than or equal to num. So what is num? Num is square root of the maximum value which is present inside n. So we already proved that you need to check from 2 to the square root of the maximum number to get prime numbers from 2 to the maximum number. Okay. Even if you go further than this 10, that is 11, 13, 17 and all, and try to find the multiples of these numbers 11, 17, 19, you won't get any until this max number, until 100. Okay, so it's always good to check only until square root of that maximum number. Now let's get to the inner for loop. So j is initialized to I square because that's the first number the value present inside I is going to strike. So we initialize directly to I square. Okay, so j is equal to I square, which we write as j is equal to I into I. We check until j is less than the maximum number, and this is tricky. This is very important. J is equal to previous value of j plus, not multiplication, plus the value present inside I. So if you add I to it, you'll keep getting the multiples of I, and we store 0 at that position because it's multiple of I. So striking off means we are storing 0 at that location, which means it's composite number. Okay, so at the end we just print all the positions, that is index values of array elements which has 1 as its value. So let's write the program using our code editor. We assign 101 to macro n, that's size of the array from 0 to 100, 101 elements. So using designated initializers, I'll initialize 1 to all the elements from index 0 to n minus 1. So all these elements will have 1 as its value. That means we assume that all these numbers from 0 to 100 are prime numbers. 1 means prime numbers. So initially we assume like that. So this is designated initializers. It's a very interesting topic. You can see the link on your computer screen. Please visit that and watch that short video. So I'll take two more variables, I and j, for loops. So we don't have any errors, just that we have not used all these variables, we have just declared. So let me take this outer for loop and start with 2, because 2 is the first prime number, and iterate this for loop until I is less than n, and for each iteration of this for loop we will increment the value of I by 1. So we could optimize this condition. So I'll take math.h library because we need that to make use of square root method, and instead of using square sqrt of n, which creates little overhead, because for each iteration of this for loop it needs to go to this math.h library and find square root, which is not necessary. Let's calculate that only one time by using a variable and then initialize the value, that is square root of n, to that number, and then use this integer variable num in the for loops condition, that is I is less than or equal to num. Okay, this optimizes the code a lot. So if a of I has 1, okay, if the value is 1, then we check all the multiples of I and store 0 there. Okay, so let's write another for loop to find all the multiples of value present inside I. So I value is index value. Okay, so let's initialize j as I square. We know that already because the first value which the value present at I is going to strike is I square. So we could use power of I comma 2. POW is present inside math.h library, or else I could simply use I into I. I want to keep things as simple as possible. So iterate this for loop until j is less than max value. So this is important. J is equal to previous value of j plus, okay, it's plus I. So if you add the value of I, you will keep getting the multiples of I, and at that location we will store 0 because it's multiple of I, which means it's a composite number. Okay, that's it. That's all the logic here, nothing else. So let me output a nice message onto the console window, that is prime numbers from 2 to, it's actually 2 to n, so I'll write 2 to %d are the value of %d is present inside n minus 1. Okay, you can change the value of n and find prime numbers from 2 to n. So I'll also print the method that is Sieve of Eratosthenes. So it's spelled as sieve. You already know what is sieve. It's an utensil to separate between things you want and things you don't want. And Eratosthenes is the name of Greek mathematician who found out this method to find prime numbers. Okay, so let me print all the numbers, all the elements, actually all the index numbers of element where 1 is present. So let me have a if condition inside here. So if a of I, you can write in different ways. You can write not equal to 0 or else equal to 0. So wherever there is 1, that position is prime. So we will be printing the value of I. Okay, so instead of a of I is equal to 1, you could just write a of I. That means a of I, if it holds 1, it means true. If it holds 0, it means false. So only if it's true, printf will get printed. So let's check that. So as you can see, it's printing all the prime numbers between 2 and 100. That's great. So we can go ahead and change this to 1001, 1001. So it will be generating all the prime numbers between 2 and 1000. Okay, you can check all these numbers. These are prime numbers. Okay, I'll give it one more try. I'll print all the prime numbers from 2 to maybe 500. So we need to take 501 here because the numbers 0 to 500 means it has 501 elements. Okay, so you could check these logics once again. So all the elements will have 1 at the beginning, and then we start storing 0 at all the positions which are multiples of I. So how do you find multiples of I? By just adding the value of I to the previous value of j. So what's the initial value of j? So the initial value of j is I square, because I square is the first number which will be struck off by I. You can even write this j is equal to j plus I as j plus equals I, which means j is equal to j plus I. So these are the notations used by experienced programmers. You can find all such syntaxes in GitHub. So that's why I keep showing these syntaxes. So these are the prime numbers from 2 to 1000. Let's make it 501 now. So you'll be getting prime numbers from 2 to 500. So these are the prime numbers from 2 to 500. So this is how you can find all the prime numbers from 2 to n using the method that is Sieve of Eratosthenes. Okay, so follow the link present in the description section of this YouTube video for source code, notes and discussion about this topic. Please share this video with your friends on WhatsApp, Telegram, LinkedIn, Twitter, Facebook, etc. And please do not forget to like this video on YouTube. Thank you.